What's good, everybody? In our last video, we have explored some pressure, temperature, and volume relationships on how gas particles will kind of act in its container. The first kind of law that we talked about was this is called Boyle's law. So Boyle's law, this is denoted as P1 times V1 equals P2 times V2. And what this basically means is that if you increase the volume of a container, then the pressure will go down. But if you increase or if you decrease the volume of a container, the pressure will go up, because when you decrease the volume of a container, the gas particles will hit the wall more often, as the size of it is lower, so the time it takes for the particles to hit the wall is lower. And another law we talked about is Charles's law. Charles's law is basically when you have temperature, you're given temperature and volume in kind of a constant pressure. And as volume goes up, the temperature goes up. If you decrease the temperature, the volume will go down. So volume and temperature are directly proportional, unlike our last law we talked about, the last law we talked about, which was Boyle's law. Boyle's law was indirectly proportional, but Charles's law is directly proportional. And the formula is V1 divided by T1 equals V2 divided by T2. So if you're given volume of one container, volume and temperature of one container, and either volume or temperature of another container, you can solve for either the volume or the temperature. Another law we talked about was Gay-Lussac's law. And we saw that, as kind of you increase the temperature, the gas particles start to move faster. They have a greater average kinetic energy. And this causes the gas particles to exert a higher pressure. Why? Well, one of two reasons. First of all, when the gas particles are faster, they hit the wall with more force. And second of all, because the gas particles are faster, they hit the wall more times. There's more collisions. So you can say that as temperature goes up, pressure goes up. Temperature goes down, pressure goes down. And this means that temperature and pressure are directly proportional. The formula for this is very similar to Charles's law, and this is denoted as P1 divided by T1 equals P2 divided by T2. And one way to remember all of these gas kind of formulas, because it can be really confusing sometimes, is you can say that Boyle is running for VP. Charles is watching this on TV. Gay-Lussac got a lot of TP, toilet paper. So you can see how, the variables in the formula are kind of in, the thing I just provided. Now we're going to talk about a topic called ideal gases. So ideal gases, they follow something called the kinetic molecular theory, which is just like assumptions about how gas particles might behave. And let's talk about the kinetic molecular theory. So the first kind of postulate in the kinetic molecular theory is that gas particles are so small, so the volume of the gas particles in the container are so small that the volume of the gas particle is basically zero compared to the volume of the container. The second law, this basically states that if a particle hits the wall, or it hits another particle, the collisions are perfectly elastic, and this means that no kinetic energy is lost. The third law states that there are no attractions between the gas molecules or the gas particles. So if a molecule hits the wall, it doesn't lose energy. It just keeps going. And finally, the last law is that the fourth postulate of the kinetic molecular theory is that the average kinetic energy of the gas particles is directly proportional to the Kelvin temperature of the gas. And finally, the gas particles are in constant random motion, colliding with the wall or each other, and the collisions with the wall, that's what causes the pressure exerted by the particles. So the reason why we're looking at ideal gases is because this is the model that accounts for gas behavior, macroscopic gas behavior at the level of individual particles. Now, you can see all these postulates. There's all these assumptions about ideal gases, how gases should behave. But, in reality, that doesn't really quite hold up. So, some gases in reality don't follow some of the rules of the kinetic molecular theory. And we call these gases real gases. All gases in the universe are not ideal gases. They're never going to be ideal gases. But there are some things we can tweak that can make a real gas similar to our ideal gas. And let's talk about it. So there are two postulates from our kinetic molecular theory that don't quite hold up in reality. So the first postulate that doesn't really quite hold up is the one about gas particles that are super tiny. The one that states that gas particles are so small that compared with the distances between them, that the size of the individual particles, the volume of the individual particles that they're in is so big, the volume of the container they're in is so big that the individual particles have basically zero volume. And while in reality, gas particles, they do have volume. And you can see this under low pressure, where the piston's not really pushing on the gas particles that much. The gas particles don't really occupy that much of a volume. They still do have a tiny bit amount of volume compared to the volume of the container, but not really that much. However, if you push down the piston, so this is an example of high pressure, you can see how the gas particles, they actually do occupy a volume, a pretty sizable volume compared to the volume of the container. You can see how the particles, the gas particles, when we were talking about that, the individual particles have zero volume. This isn't true in this case because they do occupy a significant portion of the container. So under low pressure, so when there's not much, when there's a lot of volume, the gas particles behave more like an ideal gas. Why do they behave more like an ideal gas? Because, well, they're not actually occupying that much volume in the container. And in addition, if the container is big, the gas particles are more spread out apart from each other, which means that, well, they can't really interact with each other by intermolecular forces. And this connects to the next postulate that's not really holding up to reality. So the particles, the postulate about the particles are assumed not to repel or attract each other, this isn't true because particles have intermolecular forces. And say that we have a container with low temperature. Yeah, the gas particles, this gas particle right here, is going to feel the pull, kind of the attraction of two other gas particles. And this will affect kind of the pressure, because if the gas particles are attracting this one gas particle and the one gas particle is about to hit the wall, it's going to hit it with less force because it's being attracted one way, but it's moving the other way. So the pressure is going to be less. And you can see that a real gas, kind of behaves more ideally under high temperature and low pressure. Why? Well, we already said about the low pressure that, under low pressure, we know that the volume is really big. So the gas particles don't really occupy a significant portion, and that the particles are more spread out because of the giant volume. So therefore, they don't really have, intermolecular forces with each other. But real gases kind of deviate from ideal gases behavior when there's low temperature and high pressure. Now we know that in low temperature, the average kinetic energy of the gas particles is lower, meaning that they pretty much move slower. And if the gas particles move slower, they're going to have more chances of interacting with one another. So more intermolecular forces coming into play. And there's also high pressure, because we know that when there's high pressure, the gas particles actually do take up a significant portion of the container. And we know that if the volume of the container is very small, aka the pressure is very high, the gas particles are going to be closer together. They're going to be more clumped up together, meaning there's going to be more intermolecular forces. I hope y'all enjoy the video. See you in the next one. Have a nice day.